So now we're going to introduce the Grignard reagent, and this is very useful for the preparation of alcohols, and it also introduces a carbon-carbon bond into the substrate. Victor Grignard was a French chemist. I think he began as a mathematician and won the Nobel Prize in 1912 for his work using organomagnesium compounds and the developing the reagent, the Grignard reagent. To make a Grignard reagent, we begin with an alkyl halide, and in a solvent like ether or tetrahydrofuran, which is another type of ether, we react magnesium metal with the alkyl halide to form the organomagnesium halide. And this can be any of the halides. So I said any halide, but it's chlorine, bromine, and iodide. Fluorine, alkyl fluorides do not form Grignard reagents. And we can use either a alkyl halide or an aryl halide to make a Grignard reagent. So both are capable of forming the Grignard reagent. Now, in general chemistry, we learned that a bond between a metal and a non-metal will be ionic, and this bond has a significant ionic character. It's not truly ionic, but it has a significant ionic character, and it will behave as if this is a carbon ion. It does not actually generate a carbon ion, but for our purposes, it'll probably be simpler to think of this as a carbon ion. It will also behave as a strong nucleophile and as a very strong base. So if you're in my lab section this semester, we will prepare a Grignard reagent. We'll prepare phenylmagnesium bromide, and we will use that in the prep of triphenylmethanol. So like the lithium aluminum hydride reaction, where hydride is the strong nucleophile, in the Grignard, with the Grignard reagent, the carbon ion is acting as a strong nucleophile as well as a strong base and will attack the carbonyl. And this will result in a new carbon-carbon bond. So we're going to pick up this R group here, and we will form an alkoxide ion. And in the workup step, we will have a proton transfer from a protic solvent to give our alcohol with the new R group. So this is really significant because we can significantly modify the structure through the choice of our R group when we make our Grignard reagent. So the Grignard reagent as a strong base needs to be protected from exposure to water or alcohols, any protic solvents. If we expose the Grignard reagent to a protic solvent, we're going to form the alkyl group corresponding to the original alkyl halide, just without the halogen present. This means that the reactions need to be performed in anhydrous ethers. Water has a solubility in ether, so anhydrous ether has a very low water content, and even the glassware that we will use will typically be oven dried to remove the adsorbed monolayer of moisture that is present on the surface of glass. For the same reason, the workup of the Grignard reagent is where the protic solvent is introduced to affect the proton transfer step, and it also means that the substrate can't contain acidic hydrogens, so no carboxylic acid groups or alcohols, because they will consume the Grignard reagent. Now, what's shown here are three different examples of a Grignard reaction product. So in the first, we have cyclohexanone reacting with methyl magnesium bromide, and we add the carbanion at the carbonyl carbon, forming the methyl group and the oxygen of the carbonyl converting to become the alcohol. So that's a reaction with a ketone. In this case, we have reaction with an aldehyde, again using methyl magnesium bromide, and we form the alcohol and we have a new carbon-carbon bond. In this case, we have an excess of methyl magnesium bromide, and we're adding to an ester, and we form the dimethyl analog of that alcohol. And this is going to be analogous to what we saw with the lithium aluminum hydride reaction, that we're the first equivalent of the Grignard reagent is going to kick off the alkoxy group here to form an alcohol. That's where this methanol comes from. And then the resulting aldehyde will react with a second equivalent of the Grignard reagent to put the second methyl group in place. So I mentioned that acidic protons are not going to be compatible with the Grignard reagent. So this hypothetical, we have starting with 3-bromopropanol or 3-bromopropan-1-ol reacting with magnesium. This is hypothetical. It can't actually be formed. We would not make this reagent because the alcohol can act as an acid. So if we have an alcohol moiety, we need to protect it from reacting. So we'll introduce a protecting group onto the alcohol. The first step is to do the protecting group chemistry and convert this alcohol into a non-reactive group, then to perform the Grignard chemistry, and then to deprotect the alcohol to get back to our desired compound. Now, a facile protecting group for alcohols is the trimethyl-silyl group, or TMS. So in this case, we will convert the alcohol into a trimethyl-silyl ether. And this ether linkage is going to eliminate our acidic proton and allow this this compound to form our Grignard reagent. When we do the chemistry to make the trimethyl-silyl ether, we need to include a base. We're going to use trimethyl chloride as our reagent. So what we're going to end up producing is a mole of HCl when we form the silyl ether. So we're going to include an amine like triethylamine, which can neutralize the hydrochloric acid that's produced. So in the protection of the alcohol group itself acts as a nucleophile and goes through backside attack on the silicon atom. And this figure attempts to show that with silicon, the bond length between the substituent carbon groups is longer than in the carbon-carbon bond length. So the steric hindrance is much less, that a nucleophile can get in to this tertiary silicon atom for a backside attack. Then after our reaction is complete, the trimethyl-silyl group can be removed with either acid or fluoride ion, and tetrabutyl ammonium fluoride, TBAF, is a common reagent to supply fluoride ions. So connecting these last couple of slides into one scheme, we have our compound that we want to make a Grignard reagent from, but it contains an alcohol. So we're going to protect the alcohol with trimethyl chloride with some triethylamine to scavenge the HCl that's generated. And we're going to generate the carbon chain that we're going to then react with magnesium to form the alkyl organomagnesium halide. And that is then going to react with our carbonyl containing compound. So we're going to introduce the carbon-carbon bond, this string onto this carbonyl carbon, as you see here, and then deprotect the alcohol using tetrabutyl ammonium fluoride to have the desired diol as the product.